Hi everyone, welcome to Math 256. This is Scott. Let's get started. So, Math 256 is differential equations, and where we're going to start is by figuring out what exactly that phrase even means and what it is useful for. So, we're going to start in section 1.1 of your free OER textbook, the one that's online. And this section is called Modeling with Differential Equations. All right, so let's start with just a reminder of what calculus is all about. So in calculus, in particular in differential calculus, that's calculus 1, what you learned to do was to take a known function and take its derivative to find its rate of change. The purpose of differential equations is actually the reverse of that. So it is not very often in life that we are able to actually immediately formulate a function for a given quantity. What we can often do, though, instead, is we can formulate a relationship that dictates how that quantity is changing. And then the task of differential equations is to essentially figure out what function it was based on its rate of change. So, a differential equation. So a differential equation, which is what we are up to in this class, is an equation that involves the derivative, or possibly higher order derivatives, of an unknown function. So this is an equation that involves the derivative and it could be higher order, so it could be second derivative, third derivative, or any combination of them really. The derivatives of an unknown function. So for example, what we can have is something like this. Dy dx, or we'll also write y prime frequently. We will alternate between the various notations that are common for derivatives. This is the Leibniz notation, and we can also use the primes, which is more in the style of Newton, or when it is a specifically derivative with respect to time, we can also sometimes use a little dot as to indicate the derivative. But these all mean the same thing. It's just they are more useful in different situations. So 2xy squared, for example. So dy dx equals 2xy squared. So notice here we are taking the derivative. We have on the left side the derivative taken with respect to x, and on the right side we have an expression that involves both x and y. So you may think that if you want to undo the derivative here and find the original function, you may think, oh, maybe if I just integrate it. But if you think about how that would have to work, you'd have to integrate it with respect to x, and the right side, it's easier said than done. It turns out integration is a powerful tool for finding these unknown functions, but it's not usually so simple as just taking a straight up integral of both sides. Usually we have to do something a little bit fancier in order to get it ready. But that's what we'll be learning about really starting next section. For now, what we're just going to do is figure out what differential equations are and figure out what it is that we are supposed to be able to learn how to do with them. So to solve a differential equation means to find the unknown function. So solving, or a solution A solution to a differential equation or as we may write diffeq like that for ease of writing. So a solution to a differential equation, or diffeq, is a function that satisfies the equation. Now, a function that satisfies it implies that there may be more than one, and that is in fact the case. For a differential equation, in general, there will be a family of solutions, and it will be an infinite family, and those will have constants that will serve as parameters. So solutions come in families parameterized by one or more constants. Now, if we want to find a specific solution, additional information is required. And what that additional information usually comes in the form of is some specific value or values of either the function or the function and its derivatives. So an initial value problem which we will call IVPs for short. So an initial value problem, or an IVP, this is a differential equation along with an initial condition. So this is a differential equation and the values of the function and sometimes the derivatives of the function at a specific value. A specific x value is what that means. And in particular, we'll see when the values of the function will be given and when it'll be values of the derivatives of the function. It all depends on the category of differential equation that we are dealing with. And then there is a related concept, which is a boundary value problem. Boundary value problem. And what this is a differential equation, typically of higher order, so multiple derivatives, and then a couple of different values of the y. So this is a differential equation, and the function values at multiple x values, typically representing some sort of a boundary, hence the name. Okay, so here are the kinds of tasks that we can have to do. So our tasks, so the sorts of things that might be asked of you so far, based on what you know, would be things like things like this. So tasks. So one, verify a solution, and by solution I mean solution family, to a differential equation if given to you. And this is kind of reminiscent of whenever you first started learning algebra. Before you learned how to solve equations, you learned probably what it meant to be a solution to an equation and how to check it. And so the approach here would be to take all the necessary derivatives and plug those formulas into the differential equation and just confirm that the left-hand side does equal, in fact, the right side, which is, of course, what equations are supposed to do. Confirm that the equation is true. All right, so that's the first task. Before we do an example of that, let's just list out the other tasks that might be on our plate. So two. So solve for the constants, and there may be more than one, or there might just be one, in a solution family using either the initial values, because it might be the value of the function and possibly in addition to that values of the derivatives of the function, or boundary values. Okay, so let's just go ahead and look at the example that we started with. So dy dx, so the derivative with respect to x, is equal to 2xy squared. So let's just say that's our differential equation, A. So A, verify that y equals 1 over c minus x squared is a family of solutions. Okay, so here we go. So we didn't have to find this ourselves. We'll learn in the next section, so later today, how you would actually solve this differential equation. This is what is called a separable differential equation, so it's not that hard to actually solve. But we don't know how yet. But somebody has told us that this is the solution. Maybe we can't produce this, but we can at least check it. So how do we check that this is the solution? Well, we start by actually taking the derivative. Remember, this notation means to take the derivative of what is about to follow. So we can take the derivative of what has been given to us, and we can attempt to check that will match what we'll get over here on this side. So first off, let's just think about this. How would we actually differentiate this? This is some good calculus review. This is going to be the class, by the way, in which you will finally, once and for all, really learn calculus. You thought you learned calculus when you took calculus. However, you'll discover throughout this class that you didn't learn it as well as you thought you did at that time. But now, this will be the class that will seal the deal. You will finally know calculus by the end of this term. So let's think about how calculus would tell us to find this. You may remember that there is such a thing as the quotient rule, but the quotient rule is actually something that very few people keep as part of their active mathematical knowledge, and primarily because it's not really necessary. The easiest way of dealing with this problem is to rewrite it as a negative exponent so that we can use the chain rule. So if you think about how the chain rule works, remember that c here is a constant. That's why it's written as a c. So c is the constant, and this is the constant that parameterizes this family of differential equations. So the only variable in play here is the x. And the way the chain rule works is when you have a function of x, you essentially just take the derivatives from the outside in. So first off, you just kind of find out what's the outermost function here. And the outermost function is the -1 power. And so you use just the power rule, which is, remember, you bring the power down, and then what happens is you take what was inside that overarching function, and you just you leave it the way it was, and you just apply the rule of differentiation here. So the exponent gets brought down, and then subtract 1 from it. So that becomes that. But then, according to the chain rule, then you have to take the derivative of what was under your finger a second ago. So you covered up part of the function there, and according to the chain rule, now we have to multiply by the derivative of whatever we had covered up. So now we take the derivative of c minus x squared. And remember, c is just a constant, so that'll just be 0. And then as for the x squared, that's just going to be 2x. And now if we crunch the numbers here, then what we will get is negative. So this over here, that 0 kind of disappears. So we're going to have 2x c minus x squared to the -2. Okay, so let's think about this. So we took our derivative, and now let's confirm. So true or false, dy dx is equal to 2xy squared. And this is the hopeful, questionable equals that we are attempting to check here. So we just found that dy dx, we just took the derivative and discovered 2x c minus x squared negative 2. Is that truly equal to 2x times y squared? I guess really, technically, the way I should write this is the square of that. And yep, sure enough, those are the same thing. They are just a rearranged version of one another. So yes, I don't. It would be an insult to check it to have to do any more here to check this. So we can verify that sure enough, this is a solution, or this formula does give the solutions to this differential equation, or it gives at least a lot of the solutions to this differential equation. However, if we want to pin it down to a specific solution, then what we need is a specific value. So let's go part B here. So part B, let's say solve the initial value problem dy dx, so we'll just take the same old differential equation, dy dx is equal to 2xy squared, and we'll say y of 0 equals 1/2. Okay, so it has now gone from just being a differential equation to being an initial value problem because we were given an initial value, or an initial condition is another way of wording that. All right. So we already know that y equals 1 over c minus x squared. The only question is, what value of c makes this happen? So now we plug in the initial condition. So that means that 1/2 is equal to 1 over mystery c minus 0 squared. So in other words, 1/2 equals 1 over c, and you don't have to be an algebra superstar to deduce from this that c equals 2. So then that means that the solution is y equals 1 over 2 minus x squared. So that's how that sort of a task is accomplished. You just, if you are already in possession of a family of solutions, then you just have to solve for the missing values of the parameters as given to you. Okay, so note, differential equations can also have what are called singular solutions. So singular solutions, these are constant value solutions for y that don't fit into the family of as parameterized by the constant. So these are constant value solutions that don't fit the family. So these break the paradigm that the family of solutions appears to set for you, and they are other values. So for example, so they're constant value solutions, and the way these almost always work is they're constant values of y that make the derivative always equal 0. These are constant values that values of y, I should say, that cause dy dx to equal 0 regardless of x. So in our example here, y equals 0. And this is identically equal to or constantly equal to. So this is a way of writing equals if you want to get across that this is a function that is actually constantly equal to this. Doesn't happen to equal it once in a while, but is constantly equal to. So this is identically equal to or constantly equal to. So that's what it means when you do an equals with 3 bars in this context. So equals with 3 bars can also mean equivalent in other branches of math, but here specifically, when what we're talking about is a function, then the 3 bars is to indicate that we are saying that it is defined to be equal to or constantly equal to or identically equal to 0. This is a solution to uh, dy dx equals 2xy squared. And sure enough, you can see that if y is constantly equal to 0, then the derivative of y also has to equal 0. And sure enough, that would give you 0 equals 0 on both sides of this differential equation. And so it would certainly qualify as a solution to this, but it also is not a member of the family. So, so this is a solution to that, even though it is not of the form 1 over c minus x squared. So this is not equal to 0 for any value of c. And it's not only not constantly equal to 0, it's in fact never equal to 0 for any real number c and real number x, because there is no real number that you can divide 1 by to produce 0. It would have to be an infinite number. Okay, so these are an exception to the families of solutions. Every once in a while, we will, if we ignore the possibility of singular solutions, it may come back to bite us. But typically, we are most interested in looking at the families of solutions. Now, as a note, differential equations can involve higher derivatives, and how high the derivatives go is called the order of the differential equation. So note the differential equations can involve higher derivatives So in other words, like second derivative, third derivative, things like that, can involve higher derivatives, and the order of the derivative is the order of the differential equation. So for example, here's an example of a second order differential equation. It'd be something like x y double prime plus 3xy prime plus y is equal to 0. So you will learn that this is what is called a second order linear differential equation, but and in fact it's a homogeneous one, but that's beyond our current interest. Now, when differential equations don't involve any partial derivatives, and if you'll recall, what this means is, so partial derivatives, that's when y is a function not merely of one variable, such as x, but is perhaps a function of multiple variables, such as maybe x and t. And then when you take the derivative of that with respect to a single variable, that's a partial derivative. So when differential equations don't involve any partial derivatives, they are called ordinary differential equations. Ordinary differential equations, or ODEs. When they do involve partial derivatives, they're called partial differential equations. They are partial differential equations, or PDEs. So an example of a PDE would be something like, so maybe you have the second derivative of y with respect to t is equal to k times the derivative of y with respect to x, something like that. So you've got y, which is a function of both x and t, and so it is differentiable with respect to either of those variables. And so your partial differential equation will involve derivatives with respect to one or the other of the variables. So these are beyond the scope of this class. So this course will only look at ODEs. Partial derivatives are a bit harder than ordinary derivatives, which means partial differential equations are a lot harder. than ordinary differential equations, and it's a more advanced topic that that you'll have to take another class to learn about. All right, now when it comes to when it comes to higher order differential equations, that's when we start requiring either more initial conditions or else boundary values. So higher order diff EQs, diff EQs or differential equations. Uh, so they they produce solutions with multiple constants, and they require multiple values to solve, which means in the case of an initial value problem, you need the function value as well as some of the values of the derivatives. And in the case of a boundary value problem, you need multiple different values for the function at different x values. All right, let's try a couple examples in this vein. So we'll have a couple initial value problems and a couple of the boundary value problems. So let's say that for the following, we are going to first verify that they are solutions, and then secondly, we're going to use the initial conditions or the boundary values to solve for the constants. So example. So verify gives the following solutions and solve the corresponding initial value problems, that's IVP, or boundary value problems. So all depending on what kind of information is being given to us. All right, so that'll be just general purpose explanation here. Okay, so to start with, let's go with something like this. So A. So we'll go y prime is equal to negative 7y. We are going to be given an initial condition of y of 0 is equal to 2. And then we're going to take as our family of solutions y is equal to c e to the negative 7t. So these are the three things that are given to us. A differential equation right here, a value, an initial value, and then a family of solutions. Okay, so this is an initial value problem, and so we can proceed. This one is only first order, so it's considered a warm-up for the harder ones to come. All right, so what we can do is first verify this. So y prime is equal to, and if we take the derivative of this is just us figuring out, this is us just differentiating it to begin with. So dy dt, so notice the variable here is t, so we'll respect that. So dy dt is equal to negative 7 c, so c is just a constant, and if you remember a constant multiple, that will still be there in the derivative, and then e to the negative 7t. So this is the chain rule in effect here, and that sure enough is equal to y prime on this side and negative 7y on that side. So check. So yep, that is definitely that is an accurate family of solutions for this differential equation. And now for the actual specific solution that fits this initial condition, what we have is, so 2 is equal to c, so the mystery c, the c that we're out to solve, negative 7 times the value of t, which is 0. So now remember, so that's 0 in the exponent. Remember what e to the 0 is, like any other non-zero base. E to the 0 is just equal to 1. So that means c equals 2. So then that means that finally our solution is y equals 2 e to the negative 7t. All right, so that was nice and easy. First order, it only had the first derivative in it. We only had to solve for one variable, so that was very very convenient for us. All right, let's try another one. B. Okay, so what we're going to have on this one is going to be a little bit trickier. So we're going to have y double prime, so this is second order now, plus 9y is equal to 0. All right, so that's our differential equation. We're going to be given two initial conditions here. Y of 0 is equal to 3, and y prime of 0 is equal to 0. And so those are two initial conditions, and then we need a family of solutions. It won't be long before we'll learn how to solve differential equations of this sort on our own, but for now we have to have our hands held. And so since this is second order, we are going to expect there to be multiple constants here. And the way those constants will be written is c1 cosine 3t plus c2 sine 3t. Okay, so let's now first verify that this equation here does in fact define solutions to this equation up here. So we have to verify this. So all right. So if y equals c1 cosine 3t plus c2 sine 3t, then we have to ask ourselves what the derivatives as we go down the line will be. So first off, to take the derivative of this one, the constant that's in front there, that is going to just still be there, and we just have to figure out what's going to happen with the rest of it. So the derivative of cosine is equal to negative sine. The 3 is going to come out by the chain rule. And so we are going to have this for the first term, and then for the second term, we're going to have 3 c2 cosine 3t. Again, chain rule. The chain rule is in effect here. So the derivative of sine is cosine, and then the 3 gets multiplied on top of the whole previous result. And now we take the next derivative, and what do we have? We have negative. We have now, so it's going to be, sine will become a cosine. The 3 will get multiplied out again, and so we're going to have negative 3 times 3, which is 9 c1 cosine again. And then for the other one, we are going to have oops, now it'll be minus, so it's going to be 3 will come out, so it'll become a 9, C2, and this will be sine 3t. Okay, and now we have to check. So now to check. So we take y double prime plus 9 times y is equal to 0. So we'll just put in what we have here for each of these pieces. So negative 9 c1 cosine 3t minus 9 c2 sine 3t plus 9 times c1 cosine 3t plus c2 sine 3t. And does that in fact equal 0? Yep, it sure does. We can see that that's going to distribute to those two, and they will exactly cancel out those. So we have 0 equals 0. Check. Okay, so this is indeed a family of solutions to this differential equation. All right, well, in that case, we can try to pin down the specific representative of this family that fits these two initial conditions. All right, so what we have was y of 0 equals 3. So let's just think about what that will mean. So that means c1 cosine 0 plus c2 sine 0 equals 3. Now you have to remember what the deal is with cosine and sine each at 0. And if you ever forget, you can just remember the unit circle is nature's little calculator. And so remember that sine represents the y value, cosine represents the x value, and it starts right here, and you go around the circle. So the initial x value is 1, the initial y value is 0. So that means we have c1 times 1 plus 0 equals 3. So in other words, c1 equals 3. Okay, good to know. As for the other initial condition, y prime of 0 equals 0, well, let's see, we already found the y prime. That's negative 3c1 sine of 0 plus 3c2 cosine of 0 equals 0. And so once again, we can figure out, well, that's going to be 0 no matter what, plus 3 C2, and I guess technically we already know the value of C1, it doesn't really matter though. Times 1 equals 0, so then C2 equals 0. So then what that means is that y is in fact equal to not the generic C1, C2 expression anymore, but now we have specifically pinned it down to one function, the function whose C1 value is 3, C2 value is 0. So that means we're going to have 3 cosine 3t plus 0. So that's how an initial value problem, when it's of order 2, that's how that will go. You will use so you use the values that are given to you to find the missing constants C1 and C2. All right, now let's try another one here. Let's try one like this. So C. So what we're going to do is actually recycle the same differential equation, but we will now convert this from an initial value problem to a boundary value problem. So we're going to say that that y double prime plus 9y equals 0. We are going to say that y of 0, let's say, is equal to this time 4, and y of pi. So again, we are not doing we're not doing an initial value problem now. We're doing a boundary value problem where we're given the the y values for a couple of different x values. And let's say that y of pi is equal to -2. So this is so I just wanted to make a little bit spicier here, give it a little bit more grit and gristle. Okay, so our y's, we already know what the family of solutions are going to be here. So c1 cosine 3t, c2 sine 3t. All right, and the check was already done. So C above. And you will notice in your homework from the textbook that there will be recycled differential equations in there. And when that happens, make sure that you're paying attention to problems that you've actually already solved, so you don't go around having to do the same thing more than once. Okay, so the check has been checked already. Now just plug in these two values and see where that takes us. So y of 0 equals 4. Let's think about what that means. That means c1 cosine of 0 plus c2 sine of 0 is equal to 4. And once again, this just means c1 plus 0 equals 4, so c1 equals 4. Nice and easy. All right, well, what about the other one? Y of pi. And by the way, all trigonometric functions in this class and every other class probably that you will ever use calculus in will always be in radians. There is no such thing as degrees where calculus is concerned. Radians are the only measurement of angles that you will ever see. And the reason for that is that that all the formulas that you know for the derivatives of sine, cosine, tangent, things like that, those all rely on the angles being in radians. None of the same formulas can be used without modification if they're in degrees or gradients or something else. Okay, so y of pi equals -2. So once again, let's think about this. We've got c1 cosine of, now be careful here, this is not going to be pi, but it's going to be 3 pi. So it's cosine of 3 pi. So cosine of 3 pi, plus c2 sine of 3 pi. Remember, it's 3t, and this represents t here, equal to -2. Okay, so now let's see what we get. So here, what is the cosine of 3 pi? So pi, 2 pi, 3 pi. So it turns out that's the same as just the cosine of 1 pi, but it's important to make a note of that so that we don't accidentally mess anything up. All right, so right here, then what we will have is -1, and right here what we're going to have is equal to 0. So this means -c1 is equal to -2. Now earlier when I said that this was going to get this one was going to be a bit spicier, here's where the spice comes in. So notice that between this and this we have an impossibility. So c1 is equal to 2 is what we would conclude from this. C1 is equal to 4 is what we would conclude from above, or from right here. So this actually is inconsistent. Inconsistent. So that means there is no solution. All right. So that will sometimes happen to you is you will do everything right. You will follow the rules. You will play nicely, but the problem may still not cooperate. So just a warning. Not all problems, especially not all boundary value problems, can be solved. This sort of thing should not happen with the initial value problems, but with the boundary value problems, it is sometimes going to be the case. Now let's look at some of the greatest hits of ordinary differential equations. So we are going to just look at some of the more famous ones that we will occasionally come back to throughout the course. So famous ODEs. All right, so a famous ordinary differential equation comes from, for example, Newton's law of cooling. So T here is going to be the temperature of an object. Little t is going to be time. A is going to be the ambient temperature. All right, so then Newton's law of cooling expressed as a differential equation looks like this. So dt, so the derivative of temperature with respect to time, so the rate at which the temperature is cooling, or actually heating, is proportional to, so the way this is usually written is with a k, and then put a big space between your equals and your k here for a reason you'll see in a second. So it's proportional to the difference between the temperature of the object and the surroundings. So T minus A. Now, because the temperature is always approaching it, that means that actually when T is greater than A, then the temperature will be decreasing, and when it's less than A, it should be increasing. So that means that actually this constant here should be negative. Now, in order to make that very clear, it's usually written like this. So the k here could be considered to be a negative constant, but just to indicate that the relationship here is inverse. So when the difference between the temperature and the object in the room is positive, then that means the temperature of the object will be going down. You take a hot thing out of the oven, it will cool down to the room temperature, or if the temperature is below the object, or if the temperature of the object is below the surroundings, it will heat up. If you take something out of the refrigerator, its temperature will increase until it reaches room temperature. Okay, so that's Newton's law of cooling. All right, let's go with another thing from around the same era, Hooke's law. So we have an object, we have a mass on a spring. So we got a little spring here, and then little object M here, and let's just say it's just on a frictionless thing here, and then X will be how far it is from its natural point, from its equilibrium. So X will represent the distance. And this is a signed distance. So x can be negative or positive to indicate one side or the other. It doesn't really matter which one is which one you choose to make it. Uh, you can make it distance past the equilibrium, or you can make it distance before the equilibrium. Either one. It doesn't matter, but it does matter that your x is signed. So positive versus negative. And then t. So t is equal to, or t is the time in whatever units you're using, seconds by default. And then k is going to be a spring constant. All right, and then what we have here is the second derivative. So x double prime is equal to negative kx, or actually k over mx, I should say. And just a note, whenever we're talking about taking a derivative of position with respect to time, a very common way of writing that is with dots. So two dots to represent second derivative with respect to time. So what this is saying is, this represents second derivative with respect to time. So dots represent derivative with respect to time. Okay, so anyway, so what this means is the farther out it is, the spring will tend to try to restore its natural length, and in particular, it's proportional to how far it has been distended from whatever it naturally wants to be. Okay, so that's one. Let's see, another one is uninhibited growth or decay. In other words, exponential. Sorry about that. The camera cut out for a second. So I was saying exponential growth slash decay. So this, in the case of exponential growth, is the kind of thing you might see with a population, at least for some period of time. And in the case of decay, it would be, for example, radioactive decay. So the loss of mass of a radioactive substance. Okay, so the way this can be formulated is, and it can be P if it's population, M if it's mass, A if it's amount. Doesn't really matter. So we'll just say dy dt is equal to ky. So whatever the thing is, this is something that is growing when k is positive, and it's decaying when k is negative. So this is the one that we can actually figure out what a solution to this would be. So solution family here is going to be of the form y equals to the c e to the kt. So this one is actually one that can be solved by just kind of thinking about it for a second. There aren't that many functions you know of whose derivatives can be found, or whose derivatives involve basically just the original function again times some constant. But one category of functions that does do that, as you know, are exponential functions. So exponential functions with a base of e and then the k up in the exponent will produce solutions to this differential equation. And then we can modify this slightly to make logistic population growth. So it's not very realistic to expect a population, say, of bacteria or rabbits or what have you. We can't really expect that to maintain exponential growth for very long because exponential growth, as the name suggests, is very rapid growth and it will quickly overwhelm whatever the environment is. So we'll look at this a little bit more later, but the logistic population model, and here what we have is the population, and then there is a certain maximum threshold of sustainable population. This is called the carrying capacity. And what basically happens is the population starts off growing what looks to be exponential. Then once it gets to be halfway towards the carrying capacity, it starts to level off. Or maybe if the population started out above the carrying capacity, it starts to level off down towards it like that. So essentially, it kind of decays exponentially. If it starts out above the carrying capacity, it decays exponentially until it reaches it. Or if it starts out below the carrying capacity, it begins its career with what looks like exponential growth, but then as it gets closer and closer to m, it starts to level off. Now, the way the differential equation for this can look is along these lines. So dp dt is equal to, and if we think about this as our template here, we want something that's a lot like this when y is very small, or in this case p is very small, but less and less like it as p gets to be closer and closer to m. So if we think about the way this looks, we can have k, and now before the p, what we'll have is an extra little factor in here, and that extra little factor is going to represent the factor by which, or it's going to be something that'll be close to 1 when the population is small. And then as it gets closer and closer to the carrying capacity, this ends up getting closer and closer to 0, so the population growth levels off. So we're going to have P divided by the carrying capacity. So what we have here is the differential equation for logistic population growth. We'll see next time how to actually solve this and get the value, or get the formula for the population. But this is something which, when p is small relative to m, is very much like exponential growth, and then becomes less and less like that as p approaches m. All right. Now, one last little example. This is an example that actually could have come to you from really a Math 111 class. It doesn't really require any calculus. However, it's an interesting application of uninhibited growth / decay. So radioactive decay. Let's say we have some particular substance with a half-life of 10 years. A sample is down to 80% of its initial mass. How long has it been? Okay, so now let's try to formulate this in terms of a differential equation. So the differential equation. So let's just say m for mass. And t for time. So this is a case of decay, of uninhibited decay. So dm dt is equal to km. And now what we have been given here are a couple of effectively boundary conditions. So let's just say that the initial m of 0, let's just say equals 1. 1 as in like one sample. So we are free to use whatever units we want, and so we can use the units to essentially start the mass out at a value of 1. Now a boundary value, so this comes from the half-life, will be that the mass at time 10 years will equal would equal 1/2. By the way, I should say time in years. Otherwise we'd have to make adjustments that would be inconvenient. Okay, now solution family. Well, we already know that m of t will have to be something of the form c e to the kt. What we don't know are the c and the k. So what we can do is we can actually just use the boundary values here to find the values of these two things. Okay, so m of 0 equals 1. So that means then that 1 equals c e to the 0, which means c equals 1. Nice to know. M of 10 equals 1/2, which means then that what we've got here is 1/2 is equal to c e to the k times 10. Now if I want to solve this for the c, or sorry, actually c is already solved for, so this is just equal to 1. So I'll just rewrite it as 10k. And then to solve this for the k, is what I should say, what we need to do is take the natural log of both sides. And then we can just divide by the 10. Which you could evaluate approximately using a calculator, but it's not really worth it because we are just about to try to answer our full question here. So now the question is, if m equals 0.8, t equals what? So then we just think about, all right, so m is equal to 1 times e to the k, which is natural log 1/2 over 10. times t. By the way, this can also be written as exp, which is sometimes convenient when you have these complicated exponents like this. So you can write exp natural log 1/2 over 10 times t. Okay, so then 0.8 equals that. And we just solve this by, again, taking the natural log of both sides to cancel the e. And to solve that for the t, we would just multiply both sides by the reciprocal. So then that means that t is equal to the natural log of 0.8 over natural log of 1/2 times 10. Which, if you unpack it, actually should make a whole lot of sense. So those of you who are fluent in the language of logarithms will recall that what you see right here is actually the change of base formula, which gives the log base 1/2 of 0.8, which means, in other words, it's saying it's asking like how many halvings are represented by being at 80%. In other words, how many half-lives, and then that times the length of each half-life. But in any case, so now you can just get any old handheld calculator to evaluate this for you, as long as it has scientific features like logarithms. So 0.8 divided by natural log 0.5 times 10. Just, put this into any kind of calculating device, and we get an answer of 3.2 years approximately. Now, it's not really clear in the specifics of the problem how precise some of the information that has been given to us is, so it's not really clear how many significant figures we should give. So we'll just give a couple. It's not really clear if the 80% is how precise that is. It's not really clear how precise the 10 is. So based on on a little bit of humility, not knowing how precise those are, we don't want to give our answer too precisely either. All right. Well, this was a relatively simple kind of a differential equation. If you want to learn how to solve more complicated ones, stick around for the next section of Math 256. Till then, bye.